able to join the next one. Thank you so much. So we will continue with our next speaker. He's a robotics technologist, Jeff Delaune. He's working at NASA's Jet Propulsion Laboratory, and he was actually part of the navigation team for NASA Mars helicopter flight project. He will explain the key concepts of a mission of such size, and I'm personally very excited for this talk. So please, if you can start with your talk whenever you're ready. Over to you, Jeff.
Okay, thank you. Can you guys hear me okay?
Yes, that's perfect.
Loud and clear.
Okay, fantastic. Let's get started. Well, thank you very much for having me. So this is going to be the talk about the Ingenuity Mars helicopter technology demonstration and then operational demonstration as well. So I'm Jeff Delaune. I'm a robotics technologist at JPL. If we can move to the next slide. So first, before talking about Ingenuity and Mars, I'd like to talk about like the team behind Ingenuity, because when you like design this kind of system, like it's first and foremost like a team of like men and women that just like put them together. So this was a relatively small team, like for a spacecraft, because it was a demonstration mission, so a little less requirement than for like a full-blown mission. That's just the JPL part of the team. So that's about like 100 people that you can see on this picture, mostly engineers and scientists coming from all horizons. I think pretty much all the disciplines of engineering you can see in that picture. And they were also like partner at NASA Ames in the San Francisco area, AeroVironment, which is a company in the LA area, and NASA Langley as well. If you can move to the next slide. So just a bit about myself, like as you can see, I'm just like a tiny part of that team, and I think like that's true for everyone. Like is the team first and foremost. I was born in France with an American dream. I did my bachelor's and first master's of engineering in France, and then I moved to Cranfield, where I was in the astronautics and space engineering masters for a year. Great experience. And then I moved back between ESA, Super-Héros in France, and Airbus to do a PhD in vision-based navigation. I've been at JPL for a little over 5 years now. Mars helicopter Ingenuity is my first flight project. The other big half of my time is dedicated to to research mostly on the navigation area and design of new systems that go explore the atmosphere of other planets. If we can move to the next slide. So a bit of a step back first about the 2020 mission. So this is composed of not only Ingenuity, but the rover Perseverance is actually the main goal of that mission. So whereas the previous rover was designed to find life, to find signs of current life, this one is actually designed to find traces of past life. So we want to find if life could ever exist on Mars, and if Mars was ever habitable. So that's the main science component of that mission. Now there is another component of that mission, which is to prepare for future missions. And the first future mission that is trying to prepare for is one called Mars Sample Return. That's been one of the dreams of robotic planetary exploration for several decades now. And so Perseverance actually holds a sample caching system that will enable it to take some samples of the ground on Mars, put it in some tubes. Some of these tubes will be kept on board the rover, and some of the others will be left at different sample cache location throughout the planet for either Perseverance or future rover, now currently planned to be done by ESA, to go pick up this tube, give it back to a Mars ascent vehicle, and hopefully we can get the samples back on Earth in the next decade. There's on top of that another technology demonstration on top of just Ingenuity, which is called MOXIE, and prepared to basically create O2, oxygen from the carbon dioxide that's present on Mars. It did produce its first grams of O2 last month. That's really key this time for human space exploration, because it shows that with this device, with this technology, we can produce breathable oxygen for future astronauts, but also we can produce oxygen that is to be used for the propulsion of future system, basically as the oxidizer that goes along with the fuel. So that means we wouldn't have to carry this alongside humans from Earth, and that would save a lot of mass. So now if we can move to the next slide and to the technology demonstration that is the focus of this talk here. So Ingenuity was designed at first to be a 30-day mission with the main objective to demonstrate the first powered airborne flight on another planet. And I really want to highlight that each of these words in the sentence is really important. Like it's not the first power flight. Like you had them done with the Apollo mission, and actually any Mars landing like in the past or has been like a power flight. But it's also not the first airborne flight. Like, we had Venus balloons, but if you take these two together, the first airborne and powered flight, this is the first time that's ever happened. It's also the first helicopter flight on Mars. The challenge there is to that corresponds to flying at about 32 kilometer altitude on Earth, more than 3 times Mount Everest. So that was the main challenge. Challenge number 2 is that if we could even get a first flight, which we did, was to collect as much engineering data as possible so that we can learn as much as possible about the models for helicopters and how they behave in the atmosphere, and try to create better helicopters for future science missions this time. So if we can move to the next slide. So this is where Perseverance and Ingenuity landed. So right under that yellow arrow at the bottom right, the landing has been called Octavia Butler landing. That's Octavia Butler was an American science fiction writer. The landing happened on February 18. And what's really important is that if you look at the left of the image this time, you can see what looks to be what looks like a river on Earth, like a dry riverbed, and that's exactly the same on Mars. So that's actually the main reason why we targeted this crater, is that we think that water was flowing in this area billions of years ago. You can actually see the delta and how we think the sediments got deposited, and so the rover is going to make its way up the delta and try to find signs of past life exactly in this area. If you move to the next slide. So now that's zooming in from the previous picture. So the tiny dot at the center is like the point where the rover landed. Actually, you can see that there's part of the sand is like a slightly different color. That's like the results of the thruster exhaust, like when the sky crane touched the ground. And as you could see, we were lucky enough to find an airfield, a flight zone that was compatible with all of Ingenuity's requirements right from the start. It's just next to where we landed, so that's super lucky. That's about 100-meter long area, and that was the first flight zone for Ingenuity's images. If you can move to the next slide. So I've been talking about helicopters on Mars. I mean, after all, what's so hard about it? You may ask, we got millions of drones flying on Earth. That can't be that difficult to make it on Mars. So there are a few key differences that make it at least a challenge for a small team of us. The first one is that the density of the atmosphere is about 1% of the density on Earth. And knowing that the density is what enables you to create the lift force, so that vertical force that enables helicopters to go up, or same as airplane. That means that it's for the same helicopter, we generate 1% of that vertical upward force, the lift that it would on Earth. So it's just very, very hard to get up. And it wouldn't be a big issue if you were on a smaller body that also would have a significantly smaller gravity. Mars is slightly smaller, so the gravity is about 1/3, actually 40% of that on Earth, but it's still 40%. So you got 1% of the lift, that you would have on Earth, but the gravity, is a lot more than just 1% of the weight that you have. So you still got this massive force pulling you down, while it's just much harder to get up. On top of that, which was just the aerodynamics and the aircraft challenge, you also got the challenge of any other robotic mission on Earth, which is that you're more than 180 million miles away, from Earth. That means it takes 15-minute communication one way, 30 minutes both ways actually, and it's getting larger and larger now as Mars is moving away from Earth. You also have to survive Mars temperature. It's about between -80 and -90 C. Every day, and that goes lower at night. And finally, you need to survive the rocket environment, the cruise, and the entry, descent, and landing. So if you can move to the next slide. So Ingenuity here has been our solution to all of these problems. So it's a relatively tiny helicopter, actually extremely lightweight. So it's 1.8 kilogram, but it's still 1.2 meter, from one tip of the rotor to the other one. It's got 2 of these rotors together, and it's been designed for flights up to 5 meter high, 300 meter long, and 90-second duration. If you actually look at these design specs and the kind of flights we've been doing so far, you can see that we've already gone past all of these limitations. We've flown at 10 meters. We've flown close to 300 meters, but we haven't quite passed that yet. but we've flown already like more than like close to 2 minutes. Like, so we've been like trying to explore even like past the design flight envelope of the helicopter. It's designed to be fully autonomous, so we don't have like to deal with this 30-minute communication delay. It's recharging lithium-ion batteries, the same kind of batteries you have in your phone, like through a solar panel. And actually, it's relying so much on phone technology of the shape that we also have like smartphone processors on board. Actually, the processors you have on board in Unity, like similar to, you can compare them to what you had in the Samsung S5, like so a few years back. But it's all like like basically your phone right now is most likely like more powerful than what Ingenuity has. And it's communicating with the rover directly, no direct-to-Earth communication or direct-to-orbit. If you can move to the next slide. Now there's a bit of a zoom inside, the fuselage of Ingenuity that you saw on the past picture. And so you can see, so all the computers and what we call the avionic boards on this picture are the green cards, which are disposed as a cube around the fuselage. You've got the sensors at the bottom, and the tiny orange cylinder at the center are the 6 lithium-ion batteries that you have on board. Move to the next slide. Okay, so now showing how we got to this. So this is the image of the first the first attempt to generate lift back in 2014. So that's inside the vacuum chamber at JPL. So that means that we are in the conditions of Mars on this video with less than 1% gravity. And as you can see, is that the first challenge, is that, we're actually able to generate lift and go up. Even though we're actually on Earth on this video, so we have more than Mars gravity. In the Mars density, we can't do that. If you can quickly pause the video for a second. But what you could also see is that as we did this, so there was someone outside the room trying to remote control the helicopter, and it just did crash. And if you can quickly pause the video, if possible. We can just go back to it. So that highlighted the second challenge back in 2014, which was, okay, we can generate lift, but it's just very hard to control it. And the reason why is that as helicopters basically rotate their propellers on Earth, there's tiny motions of each of the propeller, basically some flapping motion, and there's flapping around the central hub of the helicopter, but also some flapping around the main axis of the propeller that just completely change the dynamics of the helicopter. And when you do this on Mars, this introduces all kind of delays, which makes it very, very hard for a traditional human pilots or Earth-based control system to control it. So now if you restart the video and you go about 30 seconds into it, hopefully we can do that. Yeah, perfect. That's just after. Okay, so now that moves in 2016, 2 years later, where we all the controls work to understand how to control the system, and also put together you can see the system has changed drastically. Now we have much larger and thicker blades to try to limit all this disturbance motion that you have on the propellers. Hopefully you guys can hear me all right. So you can see that. So maybe move to the next slide.
Chris, could you just lower a bit the sound? Oh.
Yeah, no, that's perfect. So I will just comment on it now. So that's just to say that 2 years later, basically with a refined helicopter model with thicker blades to control this disturbance motion from the propellers and a fully autonomous control system, we were able to get that that stable flight in the vacuum chamber, which was that second video that you saw. Now that flight was still controlled using what you call motion capture cameras, so that are the same kind of cameras that you use for special effects in the movies and stuff. Not the kind of thing that you're going to have on Mars, obviously. We also don't have any GPS on Mars, so we need to have all what we call navigation system. So that was actually the part I was directly involved in. So I'm going to do a little zoom in on this specific one, and just show the 3 onboard navigation sensors that we used to basically let Ingenuity know where it was with respect to Mars, so that it could control its own trajectory. So the 3 sensors we had was a navigation camera, that's what the very tiny cylinder you see at the center here. We had a laser altimeter, something to estimate the range to the ground, and we had gyroscopes and accelerometers. So if you move to the next slide, and if you're like me, before I started to work in the navigation field, you might not know what all of these terms mean. And there's actually a very good analogy with the human body, Whereas like when a single camera is basically equivalent like to you flying with like a single eye, like not your two eyes, but like just a single one. That means because you have a single eye, like you basically lose the sense of depth and perception and 3D. Like so that means that Ingenuity doesn't know like the 3D aspects of the scene. And because it doesn't know the 3D, like it also doesn't know like how far it is, like from the terrain. It can see the rocks, but it just doesn't know how big they are. So for that, it needs like the equivalent of a ruler, like to determine the scale of the scene and the height, like so that's what the altimeter is, like so it's like basically you walking in a corridor, like with a single eye open, like and trying to find your way with a ruler, like to really understand like the scale of things in front of you. And the gyroscopes and accelerometers, like what we call the inertial sensors, is equivalent to the inner ear of the human body. And so that's what enables Ingenuity to basically determine the direction of gravity so it can orient itself properly. If you move to the next slide, please. So now that's a bit of a zoom in on the camera itself. So if you can play the video quickly, just to see like how the eye of Ingenuity works is that it's basically tracking these little features in green, which are like points of high contrast in the image. And as we take off, you're going to see that it tries to track these points in the on the image sensor. So you got like these tracks coming in, and that's what enables Ingenuity to determine the direction of motion. Like so if it's going like forward, to the left, up or down. It doesn't know with what scale exactly, like from the camera only, but that's the role of the altimeter then to determine. If you can move to the next slide. So now that's like that was like about the design. Now that's I got like a set of pictures about like what has happened since the mission. I'm going to move through them quickly, like with to make sure I fit in the 20 minutes. So there was a launch last July from Cape Canaveral. If you move to the next slide. That's like 7 months later, back in February, that was the landing on Mars. And what I want to show you is that Ingenuity is at the bottom of the rover. And as you will be able to see in a few seconds, that's a plate that gets like very, very dusty. Like at some point, you can't even see the rover. So Ingenuity was like basically in the worst place ever. Like, to see, you can see rocks flying. Like it's just really, really bad. And we had to make sure that that it can survive these conditions. If you go to the next slide. So that's how it was able to survive this. We have this debris shield that was protecting it on the bottom plate of the rover. And the rest of the video shows you the sequence of deployment, where we are progressively able to detach the connection to the rovers, pull it upright, and then start to detach it so that the helicopter basically falls upright under the rover, and then the rover can move away from it. That's unlocking the legs. Yeah, you can move to the next slide. That's fine. So that's now the same sequence as it happened on Mars, starting from early March, which was end of March and early April. So that's the drop of the debris shield under the rover. Now on J0 crater, you can see the environment around. If you go to the next slide, that's the first sequence where we start to unfold Ingenuity. First, it's about 30-degree inclination. If you go to the next slide, you see the same version now being upright. And as we do this, two of the four landing legs are getting unfolded. And if you move to the next sequence, we can see now the four legs unfolded. And then the next slide, you should see the helicopter on the ground. So that as it was about April 10th. You can also see the tracks of the wheels of the rover as we move back to deploy from it. And that was the first picture of the rover on the ground.
Hi, Jeff.
Am I still good on time? Am I seeing?
Sorry, I have to
minutes,
cut
so.
you. Yes, so if it's okay with you, if you still have time, you can join Vostok 2, and you will be able to share this presentation and finish it over there, if that's fine, because here we have to go to a break to prepare for the panel in space exploration. I'm so sorry to cut you because it's such an interesting topic. So please, if you can...
Okay, sounds good.
Thank you so much. Thank you so much for coming today.
Thank you so much.
We really appreciate it.
Crazy
So,
stuff.
as I said, we're going on a break here. We'll be back in 10 minutes. Bye. Thank you. I'm sorry.
Thank you.
Thank you. Bye.